Space warfare. Something that has always seemed to be a far-off occurrence and idea to the common person. But remarkably, its proposed methods, tactics, and ideas have existed far longer than many people realize. In the 1980s, warfare in space meant destroying Soviet ICBMs with satellites in orbit, which was the idea behind the Strategic Defense Initiative, also known as Star Wars. Now, after the end of the Cold War and the collapse of the Soviet Union in 1991, the current perceived threat and epicenter of preventive measures centers around anti-satellite weapons and cybersecurity. And then there are those people who speculate on what space warfare will have in store for us in the future. Space warfare has been a classic staple of science fiction for decades, from Star Wars to Babylon 5 to Battlestar Galactica, The Expanse, and many, many more sci-fi films, TV shows, and novels. Many of them depict one consistent thing throughout their different settings: space fighters. With the rise of the internet, discussions about the real plausibility and functionality of this role, analogous to fighter aircraft here on Earth, has spawned countless numbers of discussions and debates. Some say space fighters are useless and are a tactically and strategically dumb waste of resources. Others say one-man spacecraft will still be relevant far into the future. In addition, will space warfare usher in the emergence of completely new types of warfare? And how will those new types of warfare affect society? My name is Albert Jackinson, and I'm here to answer the following questions. Will new types of warfare emerge far into the future as a result of warfare in space? And if so, what will those be? And are space fighters practical and functional or not? In 1983, Ronald Reagan kickstarted the Strategic Defense Initiative, nicknamed Star Wars, into action. Its goal and reason for existing: to destroy Soviet ICBMs with lasers on board satellites. Space continues to be a viable asset to modern militaries. Satellites are used for communication between forces. GPS is also a huge asset as well for coordinating attacks, and with that comes the threat of other nations using anti-satellite warheads and even ground-based lasers to cripple capabilities of opposing militaries by targeting satellite optics or downright destroying them. But how will space warfare unfold in the future? Will it just be confined to satellites and cybersecurity? That depends on how relations unfold as we expand into space and eventually become an interplanetary species. And those variables can unfold in any number of ways. Arms races have always existed, and they will continue to exist. As we expand outwards and become an interplanetary species, we will need to deal with new situations and new threats. While our methods for maneuvering in combat will exclusively be based around reaction control system thrusters, no longer will they be used for precise and stable course corrections. In the heat of battle, thrusters will be used to make swift and unpredictable maneuvers. Gyroscopes are a handy tool for course correction, but they are heavy, and they need to be large to perform quick maneuvers. Plus, they need to be provided rotational energy, and that can be provided with thrusters anyway. So, in that context, using gyroscopes in combat is both impractical and is almost redundant. Smaller spacecraft will be able to turn on a dime, making combat at close ranges extremely dangerous. But what will these spacecraft look like? This is what some speculate hypothetical space fighters will look like. In space, there is no air, so wings aren't required for lift. And size in space is vital. That is why this sphere would, presumably, be extremely hard to hit due to its compact size. But there's a problem. While a sphere is indeed a compact object, a sphere is an object with a large cross-section. And even worse, a sphere is geometrically identical at every angle, which means that large cross-section will be apparent at every angle. In addition, if that sphere gets hit anywhere, essential components will likely be damaged. Engine components, radiators, etc., due to the fact its shape requires the need for crucial components to be clustered close together. A sphere also has a large volume, posing many cooling issues. Plus, a sphere is a very hard object to store in groups, and many of these problems exist for spacecraft that resemble other singular geometric objects. A cube or a triangular prism-shaped spacecraft, for example, might be easier to store, but the other problem would still exist. The ideal small spacecraft needs to be one with a small cross-section, a large surface area to dissipate heat effectively, as well as a low volume. It needs to have areas of small importance, so if it gets hit, it can still operate normally, and it needs to be easy to store. Interestingly, the ideal configuration to meet these requirements already exists. The shape of our current fighter aircraft, they are relatively flat, and they have an extremely small frontal and side cross-section, and they have a large surface area. Small spacecraft shaped similarly to today's fighter aircraft could use their, quote, wings and, quote, stabilizers as specialized heat sinks, possibly with micro solar panels integrated into the materials they are constructed of. They would be hard to hit because of their small frontal and side cross sections, and if they were targeted from above, they could easily be rotated quickly to display their smaller cross sections to whatever is targeting them, ensuring survival. If a wing gets sliced off by a laser or other weapon, they could still operate normally. With these configurations, all small spacecraft will be hard to hit, hard to cause to overheat, and be extremely maneuverable. Close-range space combat will be extremely dangerous. If combat ever gets that close in the first place, weapons in space are not hampered by air resistance, and there's no horizon either. With these two factors in mind, the effective range of weapons will be increased dramatically, and this will push combat ranges to extreme distances. The average combat distance would likely be a few light seconds. As a result, weapons will need to be developed to cope with these vast distances. Lasers would be a valid weapon of choice, but they require a lot of power, which would lead to the implementation of giant radiators. Plus, they lose energy as they travel, and the initial beam spreads out in transit, a phenomenon known as diffraction. And even though tracking a ship several light seconds away might seem incredibly hard, a computer could just fire a laser or another object where the ship will be in a certain amount of time. That is, of course, unless the ship you are fighting isn't maneuvering. If they are, then you need something a bit smarter. Missiles that come in and guide themselves to the target once they get in closer to it. Now, with all of this in mind, combat distances and the weapons that could and probably will be used, a question arises: why have space fighters? While that point may seem true on the surface, there's a catch. Those fighters don't have to be piloted by human pilots. If you remove a human pilot from the equation, that craft can pull more G's during maneuvers. It also never gets tired or passes out, and most importantly, you're not risking a pilot. Those things are also true if the human piloting it is not in the cockpit. Remotely piloted space fighters are, in many ways, taking the advantage of human pilots and drones. But if you ensure those computers are capable of complex, unorthodox problem solving, then there is an inherent risk with those AI. And if AI can solve complex, unorthodox, and unpredictable problems creatively, then they can presumably think for themselves. And if they can think for themselves, then you run the risk of something going wrong, or those AI rebelling for some reason. Thus, if you keep the AI dumb, that regulates them to less complex tasks, such as leading precision strikes against other ships. If you are sending out missiles to attack another ship, the crew on that other ship has to find a way to intercept them. And since in an arms race, you want to develop something better than your opponent, that crew might field drones to intercept those missiles, even if their intelligence is primitive. An AI algorithm is presumably going to be a guidance package every time. And then the ship that fired those missiles is going to field drones of their own to intercept the interceptor drones. Now you have drones and missiles against drones. And taking into account everything we've gone over thus far, the next logical step would be to eventually enlist part of the crew to remotely pilot drones to deal with the AI drones that were developed to counter the AI drones that were designed to ensure the protection of those missiles. Then that brings us into the issue of signal lag, and this is also caused by the immense distances between opposing ships. One of the solutions is to have a smaller carrier-like ship that deploys the remotely piloted drones closer to the combat area than the main ship or fleet, depending on what the situation is. This would make it a valuable target to disable. In this scenario, we have autonomous and remotely piloted drones against other autonomous and remotely piloted drones. Taking this arms race even further, one side may develop weapons that cannot be intercepted easily and still deliver a massive punch to targets. Pellet guns based off coil gun principles. A coil gun works by firing a ferromagnetic projectile inside a barrel, which passes through a series of electrified coils that generate a series of magnetic fields via the process of magnetic induction. These coils accelerate the projectile as it travels through the barrel. As the projectile approaches the first coil, its magnetic field attracts the projectile, and the second coil is switched on as the first is switched off, attracting the projectile through the barrel to the second coil. Again, the second coil is switched off as the third is switched on, and the projectile is attracted to the third coil. This process of switching the coils on and off in an alternating fashion accelerates the projectile to tremendously high speeds. The benefit of this for use in space as a weapon is no physical contact between the projectile and a magnetically charged surface is required, and therefore no friction is produced. This is why railguns would be unsuitable for space warfare at extremely long ranges. The friction between the projectile and the rails would be too much, and the extreme friction induced by the high acceleration required would melt any projectile. A slightly modified version of pellet cannons would work by similar principles to regular coil guns, but they could utilize an extra step to the firing process by using a concept dubbed mass stream acceleration to push a projectile along a coil gun barrel. These pellets would be able to reach tremendous speeds, depending on how much energy is put into the process, even when short barrels are involved. For instance, pellets could reach 20,000 kilometers per second with a 150 meter or a 492 foot barrel, and with 15.71 gigawatts of energy put into the process. The small 10 millimeter wide pellet would rest on a plate that is part of the barrel, and that plate and the projectile would be shoved along inside the barrel by a stream of pellets being shot at it. The concept is similar to an elevator, but with no roof at the top of the building and with no ability to slow down. This is the ideal long-range weapon of choice in space for two reasons. Missiles can be equipped with thrusters to maneuver themselves to adjust their trajectories to deal with maneuvering targets, but they can be intercepted. And lasers, due to diffraction and being inefficient in terms of power input, can be avoided by staying out of the range they'd be effective at. But pellets fired from large coil guns cannot be intercepted easily and lose no energy in transit. Lasers, though, are effective at close range, and they could be used to provide a defensive screen against incoming projectiles. Computers are smart. They could predict when a laser is going to fire and cause an autonomous drone to get out of the laser's line of fire before it fires. This makes them ideal for attacking other ships when pellets cannot work 100% of the time, and other autonomous drones could be fielded to deal with the attacking drones. That initiates a similar arms race, and drones remotely piloted by human pilots will always factor into the picture. Every weapon used for attack, whether it be missiles, small pellets, or even relativistic kinetic kill vehicles, has a counter. And the best counter of all are tools or weapons that are unpredictable. And remotely piloted drones fit that criteria perfectly. If every idea fails, human pilots will be able to adapt to any situation. That is how human pilots have managed to stay relevant on the battlefield for decades, as technology has provided a decent questioning of their viability, and that is how they will continue to be relevant centuries or even millennia to come. No matter how obsolete they might appear, human pilots will always be relevant, regardless of the era a battle is taking place in, regardless of the technology available at the time, and regardless of the situation. Next time on Science and Forward Thinking with Albert Jackinson, a return to the Societies of 2100 series.